Hello physics students, this is Dr. Brenzi and this is lesson 5.2.7, and in this lesson we're going to be able to calculate how fast a skater will spin when she brings her arms into her side. Now before I can explain that, I need to talk to you a little bit review about momentum that we learned in Unit 4, and I want to remind you that momentum is a quantity that accounts for how much an object resists change in motion. So if you have a big box and a small box, and they are both traveling at velocity v, well, one of them is going to be able to resist change in its motion a lot more than the other. And it turns out that it's the big box on the left, and we found out that the way to quantify that resistance to change in its motion, as well as its motion itself, is by using momentum, which is P equals mv. Now in physics we can do the same thing with angular momentum. You can have an object with an angular momentum I, and it's going around in a circle at an angular speed omega. So you can calculate something called angular momentum by multiplying the moment of inertia times the angular speed. So if you were to look at two identical circles and two identical speeds, when this one is more massive, then you'll notice that, well, this one will have more angular momentum than the one on the left because there's more mass. Now, some very interesting things can happen with angular momentum. Now, in physics in Unit 4, we learned about this thing called conservation of momentum, and we learned that in systems where there are no external forces on any of the items in the system, then you can say that momentum is conserved. In other words, total momentum before equals total momentum afterward. So in a sense, P total equals P total. And we had a situation before, and we had a situation after. So when you have, for instance, one case might be a collision with linear momentum, where you have a situation of before. So this is before the collision. And if you were to calculate the momentum of every ball in the system, in this case it's two balls, so if you take, you figure out the total momentum before, which is equal to m1 v1 plus m2 v2, and you'll come up with a number for the total momentum. Well, that total momentum does not change. It's going to remain the same after. So you can calculate a total momentum before the collision, a total momentum after the collision, and you will find that the total momentum, actually let me say this, the total momentum will remain conserved or the same because we don't have any external forces acting on our system during our collision. There's nobody pushing this ball to the right. It's just rolling to the right with its velocity v. And we don't have anybody pushing on this ball one way or the other. So its net force is 0. So these things are just going along with their relative velocities, and then they collide together, and we noticed that the total momentum before has to equal the total momentum after. We can do the same thing with angular momentum. Now, the most common way that you see this is with an ice skater. So if you've ever watched the Olympics or other ice skating competitions, you'll notice that ice skaters love to do spins. Okay, so what they'll do is they'll start off with their hands way out here, and they'll start even with a leg stretched out, and they go at a relatively low angular speed. So it's kind of slow, and then it becomes very dramatic when they bring their arms in, because all of a sudden they start to spin faster and fast. They spin really, really fast. Why is that? Well, that is due to conservation of angular momentum. Her angular momentum before she brought her arms in is the same as the angular momentum she had with her arms and feet in. So her angular momentum before, L, equals angular momentum afterward. So our angular momentum before equals her angular momentum after. Oops. Now you can say this, you can make this equation, or you can make this statement if there are no external torques acting on the system. We don't have anybody trying to spin our ice skater up by pushing on her sides or anything like that. All the skater is doing is she is actually changing her moment of inertia. Now, to see how that might change, let's go to actually a point. Okay, so you might remember that if you want to calculate moment of inertia for a point going around in a circle, you need to know its radius. So let's say this is a radius of 1 meter. And you need to know its mass. So let's say this is 2 kilograms. So its moment of inertia is mr squared. And that would end up being 2 kilograms times 1 meter squared. So the moment of inertia of this ball is equal to 2 kilogram meters squared. Now, if we look at another situation, let's suddenly reduce the radius to 0.5 meters. Let's keep the same ball, 2 kilograms. Well, now if you calculate its moment of inertia, you will have 2 kilograms times, now it's 0.5 squared. So you'll have 2 times 0.25, and that turns out to be 0.5 kilogram meters squared. So the ice skater, drawing her arms in closer to her body, does the same thing as taking some mass and bringing it into a smaller radius. And that has the effect of making her moment of inertia go down. So if we're not exerting any torque on the system, all we're doing is we're just bringing the mass into a closer radius, that means that angular momentum is conserved. So if we start off with, let's say we start off with an angular speed of omega equal to 3 radians per second. If we were to calculate her angular momentum, well, that's I times omega, which means it's going to be 2 kilogram meters squared times omega, which is 3, and it turns out that is going to equal 6. I'm kind of writing small there, aren't I? Let's write that a little bit bigger. So it's 6. And believe it or not, there's some really strange units for this. It turns out that the units for angular momentum are kilogram meters squared per second. Yeah, it's really strange, isn't it? Okay. Now, what happens if if I conserve angular momentum, so I have the same angular momentum. If I have the same angular momentum, 6, and I suddenly reduce the moment of inertia to 0.5, well, what happens to omega? If you were to solve this equation for omega, you'd find out that the angular speed now equals 12 radians per second. So the figure skater bringing her arms in to closer to her sides is like what happens to this ball. We started off at an angular speed of 3 radians per second, but when we bring the ball in and we conserve angular momentum, her angular speed goes up to a whopping 12 radians per second. So, if you were to think of it this way, when moment of inertia goes down, angular speed has to go up. Likewise, when moment of inertia goes up, angular speed has to go down. Okay. Now let's go on to an example that you might actually have to calculate in class. So let's say we have a 1.5 meter diameter merry-go-round, and we have a rotational inertia of 120 kilogram meters squared. So I'm just going to write some of this down on my spare piece of paper. 1.5 meters, 120 kilogram meters squared, 3 radians per second. And we have a 30 kilogram child. It says here, runs tangent to the merry-go-round edge at 2.5 meters per second in that same direction and jumps onto the merry-go-round. So what is the new angular velocity of the merry-go-round? Okay. So to me this sounds like we have a before and an after situation. So I'm going to draw a diagram before, and I'm going to draw a diagram after. Okay, so before we have, let's see if I have a circle feature on here. Yes, I do. Okay, good. Okay, so before we have a merry-go-round, and we have a little kid who is running to try to get on the merry-go-round. Okay. Oh, this is not turning out too well. Let's try that again. Let's draw the kid first. Here's the kid. Wait for me. All right, so we have our little kid running tangent to the circle, and little kid wants to hop on the merry-go-round here. Now, it gave me some information about the merry-go-round. It said it has a radius of 1.5 meters. Actually, I think it said diameter, but guess what? I'm going to change it to radius. Okay, so it has a radius of 1.5 meters. So watch out for that. I just changed the problem on you. And it has a moment of inertia I, and its moment of inertia is 120 kilogram meters squared. Okay. And it is going at an angular speed omega of 3 radians per second. Okay, so first of all, let's calculate the angular momentum of our merry-go-round. So angular momentum is equal to moment of inertia times angular speed. L equals IW. It tells us what the moment of inertia is, so that turns out to be 120. It tells us what the angular speed is, which is 3 radians per second. So it turns out the total angular momentum of our merry-go-round, it looks like that's going to be 360. And we have to put some pretty crazy units on there. Kilogram, meter squared per seconds. Let's see, does that look right? You know what, actually that doesn't look right. Hold on here. Actually it should be meters. I omega, so I, let's do that again. I is kilogram meter squared. And omega is radians per second. Oh yeah, so I did have the right units. Kilogram meter squared per second. Okay. Yeah, let's erase that to avoid some confusion here. Okay, so that is the angular momentum of our merry-go-round. Now it doesn't say that the child is pushing on the merry-go-round before they hop on. So the child's not exerting any external torque on our system here. What the child is doing is the child is trying to run to catch up with it, and then the child hops on. So afterward, we have a 30 kilogram child that hops on to our merry-go-round. And so not only do we have the merry-go-round spinning around at some angular speed omega, but we also have little Susan. Oh, little Susan, I guess. Now she's on the merry-go-round. She's sitting, and she's going wee, and her mass is set as 30 kilograms. And how far is she away from the center of the circle? Well, it turns out that's going to be the radius of the circle, which is 1.5. All right. So, what is my angular momentum after little Susie hops on the merry-go-round? Well, we know if I want to calculate total angular momentum, I have to have the moment of inertia of the merry-go-round. I'll call that I sub m. That's the same thing as this 120 right here, times omega, plus, now we have to think of the moment of inertia of our child, and multiply that times omega. Well, let's do that. We know the merry-go-round has a moment of inertia of 120, so we have 120 omega plus the moment of inertia of the child. Now, the moment of inertia for the child, we're going to treat the child like a point mass. And when you have a point mass at a certain distance away from the center, its moment of inertia is equal to mr squared. Okay, so we're going to have mr squared, and then we're going to bring the omega down from up here. So, total angular momentum, we have 120 omega plus the mass of the child, which happens to be 30. And then I have to multiply that by radius squared, so I'm going to multiply it by 1.5 squared. And then I have omega there. So I have 120 omega plus, if I multiply 1.5 squared, I get 2.25. 2.25 times 30, that is something like 67.5. I hope I'm right on that. I don't have a calculator around. Let's see if I can quickly grab one just to make sure that my numbers are right. Ah, here's one. Sorry for the delay here. So 1.5 squared, 2.25, yeah, I got that right. And then multiply it times 30. 67.5. All right, so my mental math is correct. All right, sorry for that delay. Okay, and then we have to put omega at the end since we haven't done anything with that. Well, if I add 120 omega plus 67.5 omega, that's 187.5 omega. Okay. Now, conservation of angular momentum says that what I should have on the left-hand side of this equation is the same as what angular momentum I started off with. So, when I say L total equals L total, according to conservation of angular momentum, that tells me that the 360 from before equals 187.5 times omega. And if I do a little bit of number crunching here, I should get a number that's somewhere around 1.5 or maybe even closer to 2. 1.92. All right. So 1.92 equals omega, which tells me that after the child jumps on, the new angular speed is 1.92 radians per second. Okay. Now, let's see if that makes sense. Do you think that if a kid jumps on, catches up with this, and jumps on without exerting any additional torque on the system, it started off at 3 radians per second, would you expect the child to cause it to speed up or to slow down? Well, as long as the child's not doing any pushing, I would expect it to slow down. And it turns out that's exactly what happens. It slows down, from 3 radians per second down to something around 2 radians per second. Okay. Okay, ladies and gents, well, that's an example of angular momentum and conservation of angular momentum in work. When you come in tomorrow, we're going to do some practice on this and learn how to apply this to different situations. And I'll look forward to seeing you then. Bye.